Ever wondered how multiple outputs work in digital logic and design? Today we're going to delve into that very topic. Imagine a single digital system, like a complex network of roads, each leading to a different destination. These destinations represent various functions, signals, or states of the system. Now, designing these multiple routes requires careful consideration and strategic planning, much like our digital system with multiple outputs. So, ready to explore the fascinating world of multiple outputs in digital logic and design? Alright, buckle up. First, let's understand the different types of outputs: independent and dependent. Independent outputs are those where each output is determined by a unique set of input conditions, each representing a distinct function or signal. Imagine a digital clock. The hours, minutes, and seconds are independent outputs, each determined by its own set of conditions. On the other hand, we have dependent outputs. These are outputs that rely on the state or conditions of other outputs. Consider a simple calculator. The result displayed depends not only on the numbers entered but also on the operation selected. So the output result is dependent on other outputs. In both cases, the key is to clearly define the functionality of each output and its relationship to the overall system. This helps in understanding whether the outputs are independent or if there are dependencies between them. Now that we understand the types of outputs, let's look at some key considerations when designing circuits with multiple outputs. When designing circuits with multiple outputs, there are a few key factors to consider. One of the first things to take into account is the functionality of each individual output. You need to clearly define what each output is supposed to do within the context of the overall system. Is it going to represent a certain function or signal? Or perhaps it indicates a specific state of the system? Understanding the role of each output in the grand scheme of things is fundamental. Next, consider the interdependence among these outputs. Are they independent, each determined by a unique set of input conditions? Or are some outputs dependent on the state or conditions of others? This dependency can influence the design of your circuit significantly. In some instances, you might need to ensure that certain conditions are met before an output can be activated. Another key aspect to consider is timing, particularly in synchronous digital systems. Each output might have its own timing requirements. For instance, one output might need to be activated before another, or some outputs might need to operate simultaneously. Understanding these timing requirements is crucial to ensure that your circuit functions as intended. The coding scheme for each output is another important design consideration. You could choose binary gray code or other coding methods depending on the application. The chosen coding scheme can affect the complexity and efficiency of your circuit. You also need to consider the possibility of shared logic elements. In combinational circuits, different outputs might share common logic elements. Designing and optimizing these shared elements can help improve the efficiency of your circuit. Lastly, consider the possibility of output multiplexing. If outputs aren't needed simultaneously, they may be multiplexed onto a shared bus or line. This allows for a more efficient use of resources. As you can see, designing circuits with multiple outputs is a multifaceted task. It requires a deep understanding of the system's requirements and a methodical approach to design. But with careful consideration and planning, you can develop a circuit that meets all its intended functions. Now that we know what to consider, how do we code these outputs? Output coding is crucial in digital logic design, but what does it entail? In the world of digital logic and circuit design, output coding refers to how we represent the states or signals of our system's outputs. This coding is typically determined by the specific requirements of each output and the overall system's functionality. There are various types of coding schemes to choose from. The most commonly used coding scheme is binary coding, where each output state is represented by a unique binary number. Think of it as the language that our digital system speaks, where a series of ones and zeros can represent everything from a simple on-off signal to complex data streams. Another popular coding scheme is gray code. In gray code, only one bit changes at a time, making it particularly useful in scenarios where binary code could cause errors, such as in analog to digital or digital to analog converters. But choosing the right coding scheme is just part of the story. Once we have our outputs coded, we need to consider how these outputs interact with each other and the rest of our system. This brings us to the concept of shared logic elements. In a digital system, it's common for multiple outputs to share common logic elements, especially in combinational circuits. Shared logic elements can help us create more efficient and compact designs, but they require careful planning and optimization. Consider a digital system where two outputs, let's call them X and Y, depend on a shared input A. Instead of duplicating the logic elements that process A for each output, we can design our circuit so that these logic elements are shared between X and Y. This not only saves space and resources, but can also make our system faster and more reliable. So we've covered output coding and shared logic elements. These concepts form the backbone of effective digital circuit design, but our journey doesn't end here. Coding is done, but how do we simplify and optimize our logic expressions? Let's find out. Simplifying and optimizing logic expressions is a vital part of digital logic design. This is where truth tables and Carnot maps become our best friends. They give us a clear bird's-eye view of how our inputs relate to our outputs. Imagine truth tables as a kind of ledger. For every possible combination of inputs, they list the corresponding outputs. They're perfect for showing us what we're dealing with, but they can get a bit unwieldy when we're dealing with many inputs. This is where Carnot maps come in handy. They're like the superheroes of simplification. They take the information in our truth tables and arrange it in a way that makes it easier to spot patterns and simplify our logic expressions. In a Carnot map, each cell represents a minterm or maxterm. By grouping these together, we can simplify the logic expressions for our outputs. But what if we have more outputs than we have lines to carry them? This is where multiplexing comes into play. Imagine you're a postman with 10 letters to deliver, but you can only carry one at a time. You'd have to make multiple trips, right? Well, multiplexing is like having a magic bag that lets you carry all 10 letters at once. In the world of digital logic and design, multiplexing allows us to send multiple output signals over a single line. It's a bit like having a conversation over a walkie-talkie. Only one person can talk at a time, but by taking turns, everyone gets a chance to speak. Multiplexing relies on a control signal to decide which output gets to use the line at any given time. This way, even if we have a multitude of outputs, we can still get by with a limited number of lines. We've simplified and optimized, but how do we select and activate specific outputs? That, my friends, will be the topic of our next scene. So hang tight. We're about to dive deeper into the fascinating world of digital logic and design. Decoding circuits, flip-flops, registers, and state machines are all part of the digital logic design process. Let's delve into how these elements play their roles in systems with multiple outputs. Output decoding is essential when dealing with multiple outputs. Decoding circuits are used to select and activate specific outputs based on control signals. This allows us to manage and control the flow of information in our digital system efficiently. Now, what about when we need to store some information? That's where flip-flops and registers come in. Flip-flops are the simplest form of storage elements in digital circuits. They store and hold data, allowing us to control the timing of our outputs. Registers, on the other hand, are groups of flip-flops and are used for storing multiple bits of data. It's crucial to synchronize and control these elements to ensure the smooth operation of our system. Then we have state machines. These are devices that change their output and next state of operation based on the current input and state. In systems with multiple outputs, state machines are invaluable. They allow outputs to change based on the current state of the system, providing us with dynamic and flexible control over our outputs. So we've set up our decoding circuits, arranged our flip-flops and registers, and designed our state machines. We've woven these elements together into a cohesive digital system. But remember, each output has its unique functionality and role within the overall system. Designing circuits with multiple outputs isn't just about putting together different components. It's about understanding the specific requirements of each output and how they all interact within the system. It's about ensuring that the overall system meets its intended purpose. And as we close this chapter, it's important to remember that we're not quite done yet. We have our system, but how do we ensure everything is working as it should? The final step in our journey is testing and verification. It's crucial to thoroughly examine each output independently, making sure it lives up to its specified requirements. This involves a careful analysis of functionality, timing, and interdependence. You'll want to ensure that each output behaves as intended, under a variety of conditions. Remember, even the most meticulously designed circuit can falter if not properly tested and verified. Now you can confidently navigate the world of multiple outputs in digital logic and design. So what will you design next?